We will talk about atmospheric methane removal, which is also the name of the company which I have founded with Renault about a year ago in March 21. And this whole purpose of our company is to do exactly that, to remove methane from the atmosphere. And wait, I have to see how I get. We will do a small journey today with 12 steps. The journey is just as a quick overview, has these 12 steps, and the journey will accompany an FeCl3 molecule on its journey through its new life cycle, which it will have in our vision of the EAMO process. The EAMO stands for Enhanced Atmospheric Methane Oxidation, where AMO is a natural process and EAMO is the enhancement of that natural process. Okay, so at first we will have to produce this material, then we have to ship it, load it, convey it, sublimate it, aerolyze it, elevate it, disperse it. Then the big thing is it will catalyze something, and we already know that that will be methane, and then it will go to the ground and dissolve and fertilize the earth or the ocean. Now that was a very quick journey. Now we will do the same journey a bit slower. We will do every single step. Okay, at first we have to produce the material. We will need around 500,000 up to 1.8 billion tons of FeCl3 to be produced at probably about 4 or 5 factories all over the world. And this stuff consists of basically iron ore and salt. Both are available in abundance, so we don't really have a problem with material like many other technologies, which basically use so much material that they can't work ever at scale. But this is the highest scale we calculate, and that is still only a small, very small portion, about 1% of the current iron ore production. So we don't really have a problem here with scale. Okay, the cost is about $200 for 1 ton of iron ore, and if we produce it, we reckon that we will have a cost of 1,400 euros per ton of FeCl3. Once that's the production cost basically. Now then we have to ship that to our MRP. MRP, it's a new word, that is a methane removal platform that's out in the ocean, and it looks very much like an oil rig, but it's not an oil rig. It might be an old oil rig, but okay, we will come to that. So we go with our ship with 500 containers on it to that MRP, and then the third step is we load one of these containers on top of our MRP, and the other containers, 499 containers, will stay on the barge. Then we have 1 container on our MRP. So once that is empty, we recycle it and exchange it for another full one. So we only have up to 2 containers on top of our MRP at one time. So the most weight is always on the barge. As you can see, we are an engineering company, so we look at things from the engineering side. Okay, then on top of our MRP, we will convey that powder with a pneumatic conveyor. It will look similar to the one you see in the graphics. So the container will be stored vertically upwards, and then the conveying system will feed the FeCl3 into our sublimator. So that's the next step, sublimate. So we have this dry powder, but it is still not perfect to be put into the atmosphere because those particles will be too large. And if they are too large, then when we release them into the atmosphere, they will just basically fall down. And that wouldn't really help us, because then it will all end up in the ocean very close to our MRP, and that would not solve our problems. Therefore, we have to sublimate them. That means that we turn them into the gaseous phase. If we heat them up with a lot of energy, costs a lot of energy, And then once it's in the gaseous phase, we put it into a carrier gas, probably nitrogen, could also be dry air, but yeah, that's not quite decided, but in principle into a carrier gas. And then we release that hot gas into air. So then we mix it with a lot of air. You can see here all these industrial ventilators which will mix that hot gas with air, like 1,000 or 10,000 parts of air for one part of gas. So then it will cool down, of course, because the air is normal temperature, normal ambient temperature, 25 degrees or whatever we have. And then it will go back to the solid phase. So it will then be an aerosol, right? So, and because we have had it in the gaseous phase before, we will get really small nanoparticles, right? That's the way how we want to generate nanoparticles, because we need very small particles. Best would be between 50 and 100 nanometers. So that's what we aim for, right? So the whole sublimation process is only for making the material as small as possible. Okay. Then once we have that, we immediately elevate it to the top of our stack. I don't know how many people have watched our video on our website. Here you can see this high tower. All in all, it should be somewhere around 400 meters high. So that's going to be the highest ocean-based tower in this world, on this globe. Maybe on another globe we have one, but on this globe we will have this one as the highest one. It will be higher than the Paris Eiffel Tower, about the same height. Okay, so once we elevate it, it is up at 400 meters. There's also a lot of more information. This presentation will be available later, so you can then read all the detail. Okay, and once we are up here, we can see that it is coming out of the stack, and hopefully we have not too much wind, and therefore it will go even higher, maybe up to 600 meters, because it has still a bit of temperature in it. So, and also up there in 400 meters, it's a bit cooler. So therefore we get a bit more elevation. The higher, the better. Okay, maybe we get to 500 meters. That would be ideal if we can get that to 500 meters. Okay. Now, two important parameters we have here: the height of the stack and the size of the particles. Small as possible and high as possible. Well, that's not quite true, because we don't want to get out of the troposphere. So if we could have a stack that's over 1,000 meters, then we would stop, but we will probably not ever get there. So, okay. Then the most important thing happens. And now I will actually jump over that, because that is going to be Renaud's part. He will talk only about this step, about the catalyzation of that with the methane. And that is for Renaud to share with you. He will have the same time I have, so I will not even talk about it at all. Okay, and then rain is coming and falling and taking our material down, even though we would like it to be up there for weeks and months and even years, but it doesn't, because the rain is coming and it will bring it back to the ground. And then we will dissolve the FeCO3. In 95% of all cases, it will fall into the ocean, because we are out in the ocean, but some of it will also fall on the ground. In both cases, it will dissolve back into what it came from. Remember, we started the journey with iron and salt, and that's how the story ends. We have iron and salt, and iron, and especially iron, will fertilize the ocean and the land. It's a good fertilizer, as everybody knows. So we will have fertilization, which means we will have more growth of plants. In the ocean, of course, algae, and that will also contribute to removal of CO2, but we are not concentrating on that as yet. We are not really sure how much CO2 we can remove. So we don't really brag about that. Let's put it that way. Okay, so the conclusion which I want to make is, I only have 1 minute left, that the 4 advantages of our concept, and that is in comparison to all other methane removal concepts, not to all concepts of this world, but only to other methane removal concepts, is that we have a homogeneous gas phase reaction with high reaction rate. Then we have the multiple reuse of the iron atoms because we have a catalytic process, so it can be done again and again with the same molecule. Then we have free solar energy because the whole thing is powered by solar energy, and therefore we are out there in the hot part of the world, which is like the subtropic oceans, because there the sun is shining most. And we have the oxidation in situ, which means that the methane is actually oxidated where it resides, and we don't have to bring it back into some machine with a ventilator or something, which costs a lot of energy. We do the oxidation right where the methane is in the atmosphere. And therefore, we result in the cost of 40 to 60 US$ per ton of methane removed. So if you calculate whatever you prefer, let's say 25 in comparison to CO2, like as they say, the GWP for methane is, it's a big discussion about the GWP, but if you take the lowest one, it's 25, then we end at somewhere between $2 and $3 per ton of CO2 equivalent, which is, of course, a lot cheaper than any other method. Okay. Now I'm running out of time, because therefore I will jump over this just short in the technology readiness level. I don't know, some of you might be familiar with this concept. We are now at level 4, so we are still quite far away from being done with the development of this technology. Okay, that was my part. Handing over to Renaud.
Okay, many thanks to Evan and to your team for inviting us and giving us the opportunity to talk today. My name is Renaud de Richter. I am a chemical engineer with PhD from University of Montpellier in France. As my accent lets you know. I am working as an independent researcher, and I am science advisor in several NGOs and several startups like this one. I think I don't have to convince the audience that we really need to target methane the same way that we are targeting the carbon dioxide. And it's particular because the emissions are increasing, both anthropogenic emissions and biogenic emissions are increasing. And that's why we think that methane mitigation is very important for anthropogenic emissions, but we should also target difficult to mitigate emissions and target biogenic emissions that are increasing from wetlands due to global warming. We can remove tropospheric methane from several ways. One of the ways that have been proposed is by photocatalysis, using, for instance, titanium dioxide or zinc oxide derivatives. We can also try to enhance the methane sinks, which already exist and which are natural. The principal one is the hydroxyl radical, which already destroys in the troposphere 90% of the methane. But we can also target other methane things, and one of them is the chlorine atoms, as Oswald already told you. Other methane things are minerals, soils, plants, bacteria, and there are many other proposals for tropospheric methane removal, and you can read the publication from Rob Jackson in Stanford. Among the proposed methods to remove methane, there are the catalytic zeolites, which use air-moving devices similar to the direct air capture machines. And we have proposed solar chimneys with photocatalytic coating on the greenhouse to remove methane. But as Oswald told you, the interactions are not so favorable than in the troposphere, because it does require a gas-solid interaction between the catalyst and the methane to react, to oxidize the methane. And that also requires sufficient residence times. You have also, as methods to remove methane, you can enhance the hydroxyl radical, but there is already huge amount of hydroxyl radical in the atmosphere, so it's rather difficult. And you can enhance the chlorine atoms, and these reactions occur by gas-gas interaction, and the reactions are much faster. So you can use the type of machines we have already shown. You can target point sources, but you can also do these reactions directly in the troposphere, which is much simpler, much faster, and much bigger interactions between the two gases. The chlorine atom generations, there are many ways you can generate them, and naturally they occur from different pathways. One of them is from sea salt, which reacts with acidity from pollution, from NOx or from SO2 emissions, anthropogenic emissions. And by acid displacement in the atmosphere, HCl is generated. And the reaction with pollution finally conducts to chlorine atoms. And some scientists have done some modelization and some measurements, and they think that currently the tropospheric sink of methane by the chlorine atom is about 2 or 3% of the total methane. And they think that under the marine boundary layer, in polluted regions, the chlorine atom sink can be up to 10% and 20% of the methane removal. So the speed of reaction of chlorine atoms with the methane is 16 times faster than the hydroxyl radical. That's why it's very interesting to work with the chlorine atoms. And model simulations already show that in the atmosphere there is autocatalytic chlorine generation. A key discovery was proved about 6-8 years ago by a German team at University of Beirut in Germany. And this team was using iron trichloride or even iron oxide with HCl. And they succeed generating catalytically chlorine. And the best experiments they did was one iron was able to generate 80 chlorine atoms per hour. So it's really a catalytic system, so it's very cheap. And iron can also enhance the hydroxyl radical sink by the Fenton reaction. So you all know that there is a lot of iron in the atmosphere, which is natural. It comes from desert dust, for instance, or it comes from volcano emissions. This is natural. And also you have a lot of anthropogenic emissions of iron. This is less known. And almost all the combustion processes release iron using fossil fuels. And there is a lot of scientific evidence that the anthropogenic emissions are of soluble iron, which can react with sea salt and generate iron trichloride. Also, in order to reduce the pollution from exhaust gases, it exists since a long time fuel additives containing metals like manganese, like iron, and they are used to reduce black carbon emissions and other pollutants. And fuel additives containing iron are allowed, authorized, and commercially available, both for big industrial machines and both for ships. Bunker fuel contains residual iron, between 20 ppm and 100 ppm of iron. So already the shipping industry is releasing iron in the atmosphere. And one possible way of increasing the emissions of iron is by adding iron additives to reduce pollutants, and this will generate iron trichloride over the oceans. One of the questions is that the safety of iron chloride generation by iron trichloride. So for the moment, we cannot really answer. We know that there are many ways, natural ways, by which it is already done. It's natural. We need to assess the risk, and we also need to conduct environmental impact assessments. Of course, legal authorizations are necessary to do the field trials and to do field trials. And for the moment, we haven't yet completed the computer modeling. Sorry. So conclusions. We think that mitigation of methane is very important, but that remediation of methane, removal of methane is also necessary and complementary. There are several methods to remove methane from the atmosphere. The catalytic generation of chlorine atoms by iron 3, iron 2 catalysis could be probably the best and the cheapest method for methane remediation. The next steps we need to perform are computer modeling and environmental impact assessments, plus then after that field trials. Chlorine atoms can reduce the amount of methane, but also of several volatile organic compounds, some tropospheric ozone, which is the third greenhouse gas, and some halocarbons. So chlorine atoms generation is probably the cheapest method proposed to fight global warming, but we need funding for the research and for the assessment of safety, harmlessness, and efficiency. Thank you very much. Oh, sorry. I have some publications to show you. I have been working on other removal of other greenhouse gases. The one about solar chimneys with photocatalysis is this one, and the one I talked today is this one. Thank you very much, and we're open to your questions.